This is an op amp that I made from scratch in order to find out what exactly goes into making a good op amp. And I mean, op amps are one of the more important electronics components, but unfortunately they're one of the more confusing components, with all their datasheet parameters and whatnot. That's why I put together this video so that you can find out what exactly you need to look for when deciding on an op amp for your next project. Some of you will likely remember one of my older videos in which I made an op amp much like this one. Unfortunately, in that video, I didn't really cover what exactly the op amp was capable of. That's why I've recreated it so that way we can measure what exactly it can do. I've also purchased 6 commercial op amps in which we can compare to the DIY op amp. But before we do the comparison, let's first examine the anatomy of this op amp. Here is a recreation of the original design from that video. I recommend you watch it if you don't know how it works. But as a basic rundown, the first stage is a differential pair, otherwise known as a long-tailed pair. This is the segment that will compare the voltages on our inputs. Afterwards, it is followed up by a simple P&P common emitter amplifier. This amplifier helps convert the differential output of the differential amplifier back into a more useful single-ended output instead. There's also this small compensation capacitor here for stability, but more on that later. And finally, it is followed up with another transistor amplifier. This time is an NPN emitter follower. The 2 transistor amplifiers are there to provide a buffer to the differential amplifier front end, because it's not strong enough to drive an output load all on its own. Now let's get into the comparisons. I'll introduce each op amp. First up is the LM358, which seems to be a popular part here on SciLab. It's a general purpose op amp, so it's not particularly good at anything, but it can be used for most projects. It's also really cheap. Cheap enough that I was able to buy 50 of them for this video. Next, the TL072. It claims to be a low noise op amp with JFET inputs, although I had to wrestle with it in my microphone project. Up next is the MCP6022, which I'd say is another general purpose op amp. It's definitely better than the LM358, but also considerably more expensive. I only bought 5 of these. The next op amp is the NE5532, which is a popular choice for audio circuits on the internet. Next is the UA741, which is one of those classic ICs that is somehow still around today. Just don't expect good performance from it, at least in modern standards. And finally, we have the OPA134. This one is specifically designed for high performance audio, and it delivers with a hefty price tag. Now that you are familiar with these op amps, we will begin with the voltage ranges of them, since that is likely the most basic and first requirement that you'll need to take a look at. Obviously, make sure that the op amp's minimum and maximum supply voltage requirements are being met by your project. However, what is more interesting is how closely your output can reach the supply rails. The MC6022 is perhaps one of the most ideal out of the bunch in this case, in that it can output all the way up to the positive supply rail and all the way down to the negative rail. So, for example, if we supply the MCP6022 with a 5V supply, and then configure it as a buffer, we can perfectly output that 5V peak-to-peak sine wave on the output. We call the ability to do this rail-to-rail. The other op amps would have a problem with this. If we replace the MCP6022 with the OPA134, but keep all of the other parameters the same, our sine wave will now clip at the top and the bottom. The OPA134 can swing to within 1V of the positive rail and very close to the negative rail, but it can never reach either rail. The same goes for the others, except the LM358. It isn't rail-to-rail like the MCP6022, but it is what you may call a single supply op amp. This means that it can reach the negative rail, but not the positive rail. Here's what the sine wave looks like on the LM358. This time, only the top portion of the sine wave is clipped. This is why the LM358 is perfect for when you have a singular positive DC supply, since you won't need to make a virtual ground for those low-level signals. Anyways, you may need to search for a rail-to-rail op amp if you don't have much voltage headroom. The DIY op amp also has this clipping problem, although with some weird distortion at the bottom, but we'll fix all that later. Offsets in relation to op amps are basically undesired parasitic DC voltages that are added to the output. Let's take our LM358 and read the datasheet so we know what to expect. Under offset voltage, we will find a spec called input offset voltage, which has a typical value of 300 microvolts and a maximum of 3 millivolts. Basically, what this means is that you'll add 300 microvolts to your input signal before amplification. So, let's imagine that we have a current sensing amplifier measuring current through this 1 ohm resistor. We'll have an amplification factor of 1000 times by using a 10 ohm and 10 kilo ohm resistor. Let's now pass 1 milliamp of current through it and measure the output. Ideally, for 1 milliamp, the resistor will drop 1 millivolt. In turn, the amplifier will amplify that drop up to 1 volt. Verifying with my multimeter, we can clearly see that indeed we are getting 1 milliamp through the resistor along with that 1 millivolt drop. Let's read the output now. We somehow see 2.2 volts on the output. Why is this? Well, the circuit is working correctly, and that 1 millivolt is being amplified correctly. But the input offset voltage I mentioned earlier was being added to our measurement and then amplified along with it. So, as you can see, this input offset voltage can be a big problem for large gains in precise DC op-amp measurements. Let's try to measure the raw offset ourselves. Here's the circuit that I will be using to measure the offset. This setup would yield a clean 0 volts in the output if the op-amp were ideal. However, it isn't ideal, and our input offset voltage will add itself to the inputs. We can solve for the input offset voltage by dividing Vout by 1000. So I built the circuit up on the testing board and got started with testing the LM358. Just make sure to use closely matched resistors in order to minimize error. Anyways, sure enough, we get 1.4 volts on the output of the LM358, which equates to 1.4 millivolts of offset, which is within the 3 millivolts maximum value in the datasheet. Let's try the same thing out on the DIY board. After building the circuit, we get an output of 1.3 volts, which equates to 1.3 millivolts of offset. So it's relatively high, up there with the 358. But what causes this offset? Well, a large part of it is due to the mismatch of components in the op-amp. For example, the input transistors are not perfectly matched, and they will never share the same temperature. This causes them to have different current gains, and thus different effects of the differential amplifier. Furthermore, the bottom resistor is meant to act as a simple current source. However, it is imperfect, and variations of the voltage will change its current draw ever so slightly. The top two resistors may not be perfectly matched. All of these sources of error add up together to form that singular input offset voltage that we were talking about earlier. As expected, the more expensive op-amps have lower offsets. The TL072 has a nearly unnoticeable offset from my measurement, and the NE5532 has an offset of just 70 microvolts. Either way, the offset issue may or may not be important for your project. Sometimes you are only focused on an AC signal, and audio, for example, is made entirely of AC. So simply sticking to a coupling capacitor will remove any DC, including the offset, while keeping the AC signal intact. So really, the input offset voltage only matters for precise DC measurements. Now let's talk about the frequency response of these op-amps. The frequency response is basically how the op-amp will react when different frequencies are applied to it. Here is an example of a frequency response graph from the LM358. The basic idea is that when you apply higher and higher frequencies, the lower the gain that the op-amp can provide. The limiting factor is usually the compensation capacitor. Some of you may be wondering why we even need such a capacitor in the first place. Well, let me show you what happens without it. Here's my DIY op-amp with the compensation capacitor removed. And as you can see, I have the circuit set up in an open loop configuration, and the function generator is turned off. Already you can see the instability. Without the capacitor, we have an oscillation of 330 kHz. But as soon as I place the capacitor back, the oscillation stops. So yes, the capacitor is necessary unless you can find another way to stabilize the oscillation. Either way, we still need to talk about how the specific capacitor will affect the gain of our circuit. This is how we will test the frequency response of our op-amp. First, I will set the probes to be AC coupled in order to remove any issues with DC offset. Second, I will be using the op-amps in an open loop configuration, as in there will be no feedback at all. The inverting input will be connected to ground, and my function generator will be connected to the non-inverting input. As a proper test, I will be manually sweeping the frequency from 10 Hz up to 1 MHz. Then, I will record both the input and the output voltage peaks on a spreadsheet. So let's get to the results. Here's the bode plot for the DIY op-amp. I know some of you are scratching your heads right now, so I'll explain how this plot works. On the left side, we have gain with units being decibels. A decibel is simply a logarithmic ratio. Here's a handy equation that you can punch into your calculator. The power gain in decibels is equal to 10 times the log base 10 of the ratio between those two powers. So if, for example, we have 1 watt going into our amplifier and we get 2 watts out, we will get a gain of 3 decibels. But we recorded our data as voltages, not powers, so there's going to be a bit of a difference in the calculation. The gain in decibels of a voltage is very similar. Instead, just multiply by 20 instead of 10. Let's do another example. If we have 1 volt going into our amplifier and we get 2 volts out, we have a ratio of 2 times. If we plug it into our decibels equation, we get a gain of 6 decibels. So, when dealing with decibels, just be sure to be aware of the difference between power and voltage calculations. So, if we look back at the results, we can see that we will get a flat 60 decibels of gain until we reach about a 5 kHz input signal. 60 decibels equates to a voltage gain of about 1000, so it's really not that great. After 5 kHz, you can see that the gain drops off until it reaches somewhere around 2 MHz, where the gain is 0 decibels, meaning that we have reached unity gain, so it's a ratio of just 1. If you look a bit further, you will see negative gain, which simply means that the output signal is smaller than the input. Keep in mind that all of this is the maximum gain that you can get. With negative feedback, you can limit the gain to a certain threshold. Interesting data, but let's take a look at the other op-amps to see what an actually good frequency response looks like. For the other op-amps, I'll be using the provided charts on the datasheets. Here's how the DIY op-amp compares to the LM358. The difference here is that it has much higher gain, all the way up in the 80 decibel range. What's interesting is that they drop off at about the same frequency, a little above 1 MHz. What about the others? Well, the TL072 has an interesting curve, where it has more of a linear drop-off. A similar thing happens with the MCP6022. It has a brief flat portion, then it drops off. However, on both the TL072 and the MCP6022, the frequency reaches much further, upwards of 10 MHz. All of this talk about frequency response also corresponds with another datasheet value, which is the gain bandwidth product, or GBW for short. This value is the same as when our bode plot reaches 0 decibels. It's basically there to specify the maximum frequency that you can run a unity gain amplifier. Beyond this, you will actually start losing gain, like I did with my DIY op-amp. So, depending on your desired frequency, you will need to verify that your op-amp has the bandwidth to accommodate it. Next up, we have slew rate. The slew rate of an op-amp is basically the maximum rate of change on the output that the op-amp can handle, and it is limited by the internal compensation capacitor. Let me show you what I mean. I will be starting with a buffer, which means we will have unity gain. On the input, we will have a 1 kHz sine wave with an amplitude of 9 volts. For the op-amp, I'll use the LM358. You should expect the same square wave on the output, and that's exactly what we get. But we need to zoom in to see the effect of slew rate. Zooming in on the rising edge, we will find that the path up isn't exactly a straight line, but rather a ramp up. The slope of this ramp is our slew rate, which I measured as 0.3 volts per microsecond. In other words, the fastest that the op-amp can change its output is 0.3 volts per every single microsecond that passes. This measurement is actually slower than the LM358 datasheet claims, which reads out 0.5 volts per microsecond at unity gain. The UA741 claims the same, with 0.5 volts per microsecond. But the slew rate on those two op-amps is actually rather slow. In comparison, the MCP6022 has a slew rate of 6 volts per microsecond. On the upper end, the TL072 and the OPA134 should both have a slew rate of 20 volts per microsecond. Here's the output from the TL072, and it may look odd at first because of this bump at the bottom and the top. These bumps are caused by stray capacitance in my board, since it doesn't have the greatest layout. So just ignore the bump for now and focus on the rate of change in the linear region. I measured a voltage change of 3.9 volts over 200 nanoseconds. This equates to 19.5 volts per microsecond. So the TL072 datasheet is almost spot on with the specification. Anyways, just make sure that the op-amp is fast enough for what you are doing. As for the DIY op-amp, I measured a slew rate of 5 volts per microsecond, so it's decently fast. As another demonstration, here's how the slew rate would affect a sine wave. The purple line is the original signal, and the yellow line is the op-amp's output. As you can see, the sine wave is moving much faster than the op-amp can handle. This causes it to sort of devolve into a triangle wave. For this to happen, I ran the sine wave at 100 kHz on the 358. Noise is one of those op-amp properties that can be a huge problem when you're dealing with very small signals. Take, for example, my most recent video about that DIY microphone. The capsule provides such a small output that the op-amp noise can seriously affect the sound quality of the output. So, how do we know how much noise will be contributed? Well, let's take a look at the TL072's datasheet for an example. Scroll down to the noise section and you'll see 2 entries, input voltage noise and input voltage noise density. Starting with input voltage noise, you will see that the entry is specified with a frequency between 0.1 Hz to 10 Hz. This means that the op-amp will receive random noise input voltages of 1.4 microvolts RMS, or 9.2 microvolts peak to peak. This noise will occur randomly at all the frequencies in between 0.1 and 10 Hz, just like it's shown in the corresponding graph. But what about the other entry, the one that specifies the noise density? Well, it comes with one of the more confusing units ever created, nanovolts per root hertz. Well, on the general level, it describes how much noise there is over a certain frequency range. But it would be far more useful if we can get into an RMS value like before. To do that, you just need to do some simple unit algebra. Basically, just multiply the value by the root of your frequency range. So, if, for example, we are going to operate over a frequency between 10 kHz and 15 kHz, then we have a range of 5 kHz. To get the resulting noise over that frequency band, multiply the density, which is 21, by the square root of 5 kHz to get 1400 nanovolts RMS, or 1.4 microvolts RMS in total over our frequency range from 10 kHz to 15 kHz. Keep in mind that this result is an RMS value and only indicates those frequencies. Here's a more visual way of understanding it. From 10 Hz to roughly 800 Hz, the input noise drops off. This drop-off region is commonly known as the 1/f noise region. So, as you can tell, the lower frequencies are the noisiest. But what about afterwards? Well, after that, we get a mostly flat line. So that's why there's only really one data point at 10 kHz, because the density is the same over the rest of the line. But let's try to measure this. First, we need to measure the noise that will be contributed by our measuring device, which is this oscilloscope. To do this, simply terminate the ends together using a 50 ohm resistor. You can either use a probe or a coax. Then we'll need to pull our FFT function up to read the presence of noise at each frequency. Here's what the oscilloscope is reading. We have this rather large spike at the beginning, followed by a somewhat flat line afterwards. The flat line averages out to be about negative 88 decibel volts. To understand just how small this is, remember back to when I talked about decibels in the frequency response section. These decibels work the same, except they are referenced to a particular value. 0 decibel volts is equal to 1 volt. So we can calculate that our negative 88 decibel volts is about 70 microvolts. This flat area of noise is known as the white noise region. Now, if I zoom in on the large drop at the beginning, we can see that the noise here is much higher. Over here, I get a value of about negative 78 decibel volts. So 10 times more noisy at these very low frequencies. Either way, I hope that you can see that the oscilloscope is much too noisy to measure these op-amps, especially in unity gain. Remember that the noise is called input noise, so it will be multiplied with the gain. But I'll still try to measure it. So, to test the TL072, I configured it in an inverting configuration like shown. The gain will be 1000, so hopefully the noise will show up over the oscilloscope's noise. It's also worth mentioning that the resistors will introduce their own noise in the form of Johnson noise, potentially even more than the op-amp. That's why I made sure to use lower resistor values. Anyways, here is what the FFT shows us. The result looks similar to the first, but the white noise level is much higher, negative 67 decibel volts. there's also this odd bump at 35 kHz. This bump isn't specific to the TL072, since it also appears even larger on the NE5532. I think it might be interference from my laptop. Either way, this method of measurement is much too imprecise for a good measurement, but it does prove that the op-amp does inject noise in the same pattern that it claims to in its datasheet. CMRR is a term that many electronics newcomers aren't familiar with. Well, it stands for Common Mode Rejection Ratio. Likewise, PSRR stands for Power Supply Rejection Ratio. But let's start with CMRR. What exactly does common mode mean? Well, remember back to the beginning of the video where I showed you the anatomy of the DIY op-amp? The first input stage is a differential pair. The purpose of this pair is to amplify the difference between the two inputs. When the two inputs have the same voltage, we call this a common mode signal. And since there is no difference to amplify, ideally, nothing should be on the output of our op-amp. Let me show you an example. Here I've set up a differential amplifier with a gain of 10. On each input, I've placed a nearly identical sine wave. The only difference between the two is that one is the exact opposite of the other. Now, since they're exactly the opposite, the amplifier will amplify their difference and end up with the amplified sine wave on the output. But if I made them exactly the same, such that both inputs receive the same signal at the same time, then nothing should show up in the output, because both inputs are the same voltage. So, if we go back to the differential signal, imagine what would happen if some common mode noise came in and interfered with the circuit. What would happen? Let's make some changes to our test circuit. First, I will put our signal through this transformer. The transformer is wound to a 1-to-1 ratio. So, AC placed on the input will be mirrored on the output. The special thing that is useful about it though, is that the secondary side has a center tap. This means that if we measure from the center tap, we will get two opposite sine waves on each end. Now let's inject our noise. I put my function generator running a 2 kHz sine wave on the center tap. If you look closely on the oscilloscope, you will still see the shape of the two main sine waves that are opposite one another. But the noise on each is exactly aligned. Now, if we run these two signals through the differential amplifier, we should only see the original main sine wave on the output. The noise disappears because it is common mode, in that it is exactly the same on both inputs. Hence, common mode rejection ratio. However, the op-amp has more trouble rejecting common mode signals at higher frequencies. Here is the LM358 for example. At the start, it has about 90 decibels of CMRR, which means that the common mode signal is 90 decibels smaller than the desired signal. However, later in the graph, we see that the CMRR starts to fall off at those higher frequencies. If we go back to the testing circuit and increase the gain to 1000 times, then we can see the common mode signal start to come through. This is what the signal looks like at 1 MHz, a 1000 times amplification, and a 7 volt amplitude input. So it takes a lot just to get a common mode signal through. As for the DIY op-amp, I ran through and made this chart of our CMRR. To calculate the CMRR, calculate the gain of the differential signal and the gain of the common mode signal. Divide the gains to get a ratio. Afterwards, take the log and multiply by 20 to get a ratio in decibels. At the starting frequencies, I got a CMRR of 28 decibels, so already it's really low. Low enough in fact that there isn't much of a drop off until 100 kHz. Anyways, as for PSRR, it's a very similar concept to CMRR. The main difference is the amount of power supply noise that will reach the output. This could be an issue depending on your circuit, but oftentimes a simple decoupling capacitor solves a lot of the PSRR problems by filtering out those higher frequencies. Now, so far you've seen the DIY op-amp falling short in basically all of these comparisons. So why don't we give it a bit of an upgrade? First, let's fix our current source. Currently, we have R3 acting as our current source, but it doesn't do a great job. So instead, let's use a current mirror as our current source. Basically, when we pass current through the first transistor, the second will match that and draw the same amount of current through the second path. We can set the current by using a resistor on the first transistor, and that will stay steady since the voltage will be stable. The second will match the first because they both share the same base emitter voltage. So ideally, these should both share the same input current and thus the same collector emitter current. This new current source will improve performance because it will stay constant, unlike the resistor current source. This should improve CMRR and gain. We can use a similar trick on R1 and R2. By replacing them both with a PNP current mirror, then we can ensure that both paths have equal current flowing through them, and this will balance out the op-amp. Let's now shift our focus over to the output. Currently, I'm using an emitter follower for the output, but switching to a push-pull amplifier, also known as a Class AB amplifier, should improve performance. It will improve efficiency since only one transistor will be active at a time. Between the base of each output transistor, we will place two diodes in order to prevent crossover distortion. And finally, we will replace R6 with a proper current source in the same way that we did earlier, by using a current mirror. With these improvements, I remeasured a few of the parameters. Our op-amp has an improved open loop gain that I can't honestly measure with my function generator at lower frequencies. I would need an even lower input voltage, but I was able to measure it starting at 10 kHz, and that value started at 70 decibels. Either way, it's easy to tell that the open loop gain has massively improved since it barely broke 60 decibels on the old op-amp, and that was at the lower frequencies. The slew rate also got a big upgrade to 10.4 volts per microsecond. This is a slew rate big enough to be very competitive with the commercial op-amps. The CMRR also got greatly improved to 45 decibels, thanks to that new current source at the bottom of the long-tailed pair. At this point, the best way to improve performance even further would be to properly match each transistor so that they have a close current gain. It would also be best to thermally couple the transistors together to match thermal performance. And, obviously, produce the thing on a PCB instead of a breadboard. Either way, these improvements are still incredible. With some more work, I imagine that this discrete amplifier could have similar performance to those inside of the ICs. So, now that you know all of what these datasheet parameters mean, it's time to narrow down which op-amp would be useful for you. Let's first begin by reviewing what all these parameters would be in an ideal op-amp. An ideal op-amp would have rail-to-rail output, have no offset, have an infinite gain at all frequencies, an infinite slew rate, zero noise, and have an infinite CMRR and PSRR. And it would also be free. Now, since none of these op-amps are ideal, you have to pick which one would be best for your project. As my regular viewers know, I've used the LM358 in several projects, simply because it is dirt cheap. For most things, it's good enough. Not to mention just how helpful the single supply operation along with the huge voltage range is. However, the LM358 isn't always the best choice. Something like the OPA134 would be great if you are designing a very high performance audio amplifier. It has extremely low input noise and a very high slew rate. The only drawback would be the high price point. The NE5532 is similar to the OPA134 in that it is meant for audio applications, but it's a bit cheaper and has worse performance. For most other things, the MCP6022 would be a good choice. It's a general purpose op-amp like the LM358, and for the most part has better performance than the LM358. However, it falls behind in both price and also in operating voltage range, since it can only go up to 5.5 volts. And surprisingly, the upgraded op-amp can be a viable option if you'd like the challenge. So really, it all comes down to what exactly you need your op-amp to do, and based on that, you pick one. Either way, it definitely doesn't hurt to have a surplus of LM358s on hand. But hey, that's just my opinion. Anyways, if you've watched this far into the video, thanks for watching. If you've enjoyed up to this point, please consider subscribing so that you can see my future videos. Also, check out my Buy Me a Coffee page, because with your support, I can keep making these videos. Anyways, thanks for watching. Have a good one.